Here we have section 7.5. We'll do example 3. And in example 3, they are using another physics relationship where they say, whoops, got my hand on there, force is equal to some constant g times mass 1, mass 2 over d squared. And in example 3, we're launching something up. And so what's happening is, d starts as the radius of the Earth, but then keeps increasing. And so again, we could call that our x. We could find the force of gravity here at the surface of the Earth, but then here it's something a little different, here it's something a little different, here it's something a little different. And so we need to just estimate with little dx's. We'll have force at any given interval I is going to be our g, our m1, m2, and divided by our particular xi squared that we have here as we go. Okay, so now they mention some assumptions. So, one of these masses is the mass of the Earth. They're saying that's constant. They're saying the other mass, which would be the mass of the space module that we're trying to put into orbit, or the rocket, that's not changing. Now, so we could also have, if that's the rocket, that could also be changing with respect to x through time. Because it's burning fuel, that kind of thing. And so we could toss that into the mix. And, in all this, you could toss friction in there, at least for a while, until this thing gets out of the atmosphere. And so there are other things that could be changing, but in this particular example, they're only changing that distance d as we move along here, and that's an I. And so, we need to add that up, that force, and then times the distance. Well, that distance is delta x, and so we're going to add up all these f sub i's times our little delta x's, and I equals 1 to n, and we're going to let that n go to infinity, delta x go to 0, and so that is going to produce our integral here. And so we need to fill in all these things. So they say that C, they tell us the module weighs 15 metric tons on the surface of the Earth. Okay, so we know that F equals, and they just throw all that together into a C, so C over x squared, and we have 15 metric tons on the surface of the Earth, and they're saying the surface of the Earth is 4,000 miles, so we square that, and we get that C is equal to 15 times 4,000 squared, which again, I'm just reading from the text, and that is 240 million. Okay, so we have that. And so each one of these little forces as it changes is this 240 million divided by our particular value of x wherever we are along here. So, whatever that x value is, and then times our delta x. So that ends up making an integral, and we start at 4,000, and we end up, how high are we putting this thing up? 800 miles. So we're going up to 4,800. And we just have our 240 million, big numbers here, 240 million over x squared dx. So this is just our 240 million. So 24 times 10 to the 7th, made it a little bit shorter to write. And I do my antiderivative of 1 over x squared. Well, that means that's x to the negative 2, add 1, so we get x to the negative 1, but then also divide by that negative 1, so we get this negative. And we are going from 4,000 to 4,800. So this is equal to 24 times 10 to the 7th minus that over 4,800, and then minus a minus 24 times 10 to the 7th over 4,000. Okay, so this is minus. Well, two of the zeros can make this times 10 to the 5th. And then 24 over 48 is just a half, so I could write this as 0.5 times 10 to the 5th. And then we have plus, because a minus and a minus. And I have 3 zeros down here. That'll make that times 10 to the 4th. And 4 into 24 is 6. Okay, so I have that, 6 times 10 to the 4th. So this is equal to 6 times 10 to the 4th minus 5 times 10 to the 4th. So I just changed the 0.5 to a 5 and made that 10 to the 4th. And so that's just 1 times 10 to the 4th, or 10 to the 4th, 10,000. So it says the work done is 10,000. Now, what the heck were the units on this thing? All right, x is in miles, and so we had our dx would have multiplied by miles, but our c, I don't know what the heck the units were in all that. I guess in the end, I know that the units of this whole thing right here are, this whole thing are units of force. And, they talked about metric tons, so a lot of this sounds like newtons. Okay, so they came up with foot-pounds. I'm not sure how they, I guess the, I'm not sure, I'm looking at where they converted units, and okay, so they've got their 10,000 mile tons, right? That's what we had. So mile in metric tons. Okay, because our force, yeah, now that I remember, once I see that, our force originally was the 15 metric tons. It was in metric tons, and so miles. But now they want to change it to foot pounds, and so we would have to look up. I think a metric ton is 2,200 pounds. So I'd have to take their word for it. I suppose we can check it. So if they want to change to miles and from miles to feet, I know that there are 5,280 feet per 1 mile. So I can multiply by that and the miles will disappear. And then pounds, yeah, I think it's 2,200 pounds in a metric ton. And we can check that. So that would be 10,000 times 5,280 times 2,200. This is supposed to be decimals here. Yes. Okay. So 10,000 times 5,280 times 2,200 is 1.1616 times 10 to the 10th. And they have 1.16 times 10 to the 11th foot pounds. That's interesting. Did I do 10,000? Ah, look at there. I did 1,000. 10,000. So we have 1.16. They have 1.16. Third decimal place, they have a 4. We would have a 2. So my best guess is that the 2,200 pounds in a metric ton is just a tiny bit off. But anyway, so we can go back here and get our, by multiplying by those two things, we get our 1.6. What was it again? 1.62 is what we get. Oh, 1.162. 1.162 times 10 to the 11th foot pounds. Do LBS there for pounds. Okay, and then they do another conversion to joules, but yeah, that's just a conversion. So again, what happened was we had to come up with how our force was changing, but it's just that force times a small change in distance, and that force was based on a distance and the x squared. But we do that and we end up with the same thing they did in example 3.